So let's get started. We're only 3 minutes behind, which, as I just said, is actually pretty much on time for our standards here. So welcome everybody to today's thesis defense by Chontos. I want to say a special welcome and aloha to Ashley's parents, Diane and Jim, who are dialing in from the East Coast. Fortunately, couldn't be here, but we're happy to have you online. So welcome, and I hope you're doing well. So just as a reminder for everybody, also online, the way that the proceedings will be is that Ashley will give us a presentation on her thesis work for about 40 minutes. We'll then have questions from the general audience, everybody in the room and online. And after that, I'll ask everybody but the committee members to leave. We'll have a closed session. And afterwards, if all goes well, we'll have a celebration in the courtyard. Before we started all this, and before I hand it over, as is customary at the IFA, I will give you a little bit of an introduction into Ashley and her path that led her to today to defend her PhD here at the IFA. And those of you who know Ashley know that this is actually quite a sort of non-traditional trajectory that Ashley took in her path towards academia and astronomy, and a very interesting one, and I'll hopefully do that justice. So it starts in small towns, Saugerties, I hope I said that correctly, in upstate New York, near the Hudson, at the Hudson River, where Ashley grew up. And I heard that she was very eager to learn from a very young age and solved 500-piece puzzles when she was 4 years old. But there was another passion that she had, lots of passions, but one of them was in fact sports. So here's Ashley, young Ashley. Playing baseball and being very good at it. Apparently it's an RBI leader. But that was not the only type of sport that Ashley did. Also soccer. So here's another cover page, player of the week, playing soccer. But that was not it. There was actually more. And she also played volleyball. And here's her volleyball team in which she played. But the sports, all the talents athletically, were not the only thing that interested Ashley. Of course, science was also part of it. Here's an example. This is probably some early science fair. You can't read this, but actually, if you read it closely, it says the life cycle of a frog. So maybe that was some sort of early indication that later on she will be studying the life cycle of stars and planets, as you'll hear later today. But actually, Ashley's trajectory after high school actually went a bit of a different path, and she actually had a career in modeling for about 6 years, a very successful career in modeling, which bounced around all over the place in New York and Los Angeles, and you see some of the products of the work on the slide. But eventually, Ashley decided that that was not the future that she wanted to take, and she actually returned to college and returned to New York and got a degree at the State University of New York in Albany. And as part of this, had a undergraduate research experience, which I know, talking to her, she mentioned it multiple times, is quite instrumental in her path, working with Bruce McIntosh at Stanford University and the team of the Gemini Planet Imager, which is or was, I think, at Gemini South. And here are some images of Ashley in Chile. And you can see here in this red arrow that her passion for exoplanet science, I think, developed quite early on by hugging the G5 at Gemini Planet Imager. Of course, eventually Ashley ended up in Hawaii, here at the Institute for Astronomy. So here is some examples of the sort of shenanigans that our graduate students are up to while they are here. And that includes being having the best costumes during the Halloween parties that always seems to happen, being very cold on top of Mauna Kea, here in the top right, going hiking. I'm not sure if there's in a room what you guys are doing here, but going to the beach, of course. Drinking lots of coffee. This apparently was taken this morning, in fact. So thanks Suchi for that last-minute contribution. But there are many other hobbies actually or passions that Ashley has. One of which are furry friends. This is actually, I did not make this up. This is from her own research website. Come for the science, but stay for the caption. The cats are priorities, that's right. Cats are very important. I know that's been important in the past for graduate school. One other thing that I did not know, which an anonymous source told me, and you see this in this bottom right for pictures here, is that actually has a tendency to lock herself onto the floor, literally. I've never seen this. I'm not sure if that says anything about me as an advisor. Anyway, maybe we'll see it after the
We'll call it laughing.
Maybe after the weight of the defense is over. One other interesting tidbit I learned is that ice cream plays a very important role, actually as well. So if everything goes well at the celebration later today, we'll have a special treat for actually if things go well. Because ice cream apparently has an important role in grad school and other things as well. Those of you who know actually know that she's actually done a lot also for the outreach program here at the IFA. She was the IFA outreach coordinator for a few years. Organized numerous events, and many of our grad students do, of course, but actually was really engaged in this. And here's some examples of actually doing outreach at Astro Day on the top left and the bottom right. Also doing High Star, which is the bottom left, which is where we expose high school students to research. Of course, in the end, Ashley and I started working together, and we've actually been working together for quite a long time. So, and it happens actually that we both arrived at the IFA roughly at the same time. So this was the very first email that I got from Ashley. I had to take this out, but I still have it. And back then, I was actually not at the IFA myself. So I was in the process of moving from Australia to Hawaii. And Ashley was very proactive and reached out and said, basically wanted to see whether we can work together for a 6991 project, which eventually we did. And we ended up also continuing to work on the 6992 project and a thesis afterwards. So actually working together for 6 years, which is the longest I think I've worked with any student.
You can't get rid of me.
We'll see. But as you'll see, this time has been also very productive. And so one of the things after the 699 project, the first 2 years, was that we, of course, had to come up with a dissertation project. And it happened that at the same time, we actually had to design our dissertation project. TESS was launched, so NASA mission, NASA Space Telescope. And of course, doing this is always kind of risky, right? I mean, it's the Space Telescope, it's launched by a rocket, the rocket might explode, and then the dissertation plans go out the window. So this is actually an image in this room of us watching the TESS launch in April 2018. And you can see here the rocket taking off. And on the right-hand side, it's actually me standing on the side of the room. And one thing I noticed when I looked at this picture again was actually that it seemed like I was the terrified advisor. And actually it was very calm. So I'm not sure whether this was just on the outside, but anyway, I was quite anxious, of course, that things would go well, and they did, of course. TESS launched and everything went well, and now we have years of exciting data to work with, and you will hear about the sort of work that Ashley has done with this data later today. One other thing about Ashley that perhaps not many of you know is that she's done a lot of observing. And you will hear this again. A lot of our students do a lot of observing, but Ashley has actually spent 70 nights observing with Kepler. Now, this was not all, her PI time, just for anyone in the TAC who might be worried now. But it is observing that's being done through the California Planet Survey, and Howard is here as one of the committee members. But she spent a lot of time observing with Keck, of course, for her thesis, but also for many other science projects that go on in the collaboration. One thing I really like about these two pictures is, of course, we have Anne Bosgaard on committee here in the room. He's actually observing with Anne, our most experienced observer at the IFA. And this picture in the middle, which is actually very new, just taken a few weeks ago, where Ashley is teaching the next generation of students how to observe with Keck. And this is actually Mason, who's in the room, who's a high school student visiting us from the East Coast. Now, of course, Ashley has published several papers during her career. You've heard a lot more about this. So there are 4 published papers, 1 software paper, and 1 paper that's in the works. And you hear a lot of work about the science results in her talk. So I won't dwell on this. I will briefly say that, of course, she presented her work at various conferences. This was still pre-pandemic, but also post-pandemic. So here's some examples. This is at NASA Ames. You hear a lot more about this picture, I think, in her talk. As well as the Kepler Science Conference in California and in Cambridge, and of course also online talks during the pandemic. Her work was recognized through awards. It's one example. is the ARCS award. So the image here on the top left, showing the cohort during that year that got that award. On the top right, this was earlier this year, where I actually received the Regents Medal for Excellence in Research at the graduate level at the University of Hawaii. And she also was the recipient of an NSF Graduate Research Fellowship. She also got to do some outreach in terms of science communication to the media. So an example is here in the bottom left. This is actually an interview with HPR that resulted from one of the papers and also being highlighted in the local Star Advertiser as one of the discoveries that she'll describe today. And of course, we'll send her off after this to her next stop, and that will be as a Henry Norris Russell Fellow at Princeton University, which is a very prestigious position at a very, very good astronomy department. We wish her well on that journey. We're very proud of her for that achievement. Okay, with that, I think I've talked enough, and I will hand it over to Ash.
So much for that, Dan.
I can't tell whether that was sincere.
It was. I can take this off, right?
Yes.
Okay.
Having your coffee next to your laptop is making committee member nervous. Do you think we could put your coffee someplace? Like maybe, I don't know, someplace where you could not fall.
There's a table behind you, but it's.
Right.
Live on the edge, Mike. Come on.
I'll need this. Okay. I'm not sure how I can top that, but I will give it a try. So let's talk about what I've been doing here the last 6 years. So over the last 2 decades, precise photometry of stars from the NASA Kepler, K2, and TESS missions has revolutionized stellar astrophysics and exoplanet science. And today I'm going to take you through my personal journey of navigating this very broad landscape, discussing some of the things I've discovered and learned along the way, and also figuring out that finding accidental discoveries can apparently be a skill. So when you think about the NASA, Kepler, and TESS missions, when you naturally think of that, you probably think planet hunting mission. And while this is certainly true, we were also very good, well, they were also very good at detecting something else, which is stellar oscillations. The study of which is referred to astroseismology. And because it's going to be a recurring theme in my talk, I figured I would kind of get a brief introduction of what it is, what we can learn from it, before I start talking about the science. So I call this a crash course in astroseismology, or crashtroseismology. I know this is a really horrible joke, but like, anyway. So stars ring just like musical instruments at different pitches and tones. And it turns out that we can observe this through tiny little fluctuations in velocity space, and actually in this context here in brightness variations. Sometimes referred to as the song of the stars. This method allows us to see inside the star, and that these sound waves probe the stellar interior and provide information that is otherwise like inaccessible through other means. And while this might seem overwhelming for some of the non-scientists maybe on the line, all I'd like for you to do is qualitatively take away some of the things we can learn, as well as maybe some of the features that we're looking for. So to demonstrate this, I figured I'd start with the star that we know the best, the sun. So this is what an astroseismic detection of the sun looks like in brightness variations. This is taken from the Virgo instrument aboard SOHO. So we have the frequency in microhertz, don't ask, but this is helpful for us. So frequency on the x-axis, power density, or some sort of like power or measure of amplitude on the y-axis. So oscillations in the sun are driven by turbulent near surface processes referred to as convection. Since convection is a stochastic process, this is why you see modes over a range of frequencies here. And now I'm just going to highlight a few features and then just mention why these are important for stellar or helpful for stellar astrophysics. So the first is this regular spacing, or this kind of cone pattern. This parameter here is referred to as delta nu, or the large frequency separation. D nu actually has many names, but basically this value, this quantity here, probes the interior. Since these are acoustic sound waves, it's probing the interior, and it actually gives us a very precise stellar density. And now if we pick just a region and zoom in, just for reference, this is the characteristic frequency spacing. There's another separation called the small separation, which is cool because it constrains system ages. And then finally, the approximate shape of the envelope of oscillations is approximately Gaussian, where the peak height of this is referred to the frequency corresponding to maximum power, or mu max. And as you can see here, mu max for the sun is right around 3100 megahertz. And for those that are not used to thinking in megahertz space, which presumably is probably almost everyone, this corresponds to a convective time scale of about 5 minutes. And it turns out that mu max actually slides, so it's tied to the surface gravity of the star. So oscillations sliding to lower frequencies would indicate a lower surface gravity, and hence immediately provides information about the evolutionary state of the star. So the two parameters, d nu and nu max, are referred to as the global astroseismic parameters. And if you combine this with the spectroscopic effective temperature, you can actually very nicely constrain a stellar mass and radius using well-known or well-established scaling relations. So it turns out that I've developed and released one of the first open source packages to measure global astroseismic parameters. The reason I did this is because the software that I was using was written by my PhD advisor during his PhD, but it happened to be an IDL, and because I didn't want anyone else to have to go through that again, I ended up translating this into Python. We've also been actively developing it, and it comes with many new enhancements. So we've been trying to make it more accessible to the broader astronomy community. And yeah, so it's pip installable. We have extensive documentation. Please check it out. And especially thanks to missions like Kepler, K2, and TESS, that astroseismology has become more mainstream. And now hopefully with this piece of software, more accessible as well. All right, so now that we have that tool in our back pocket, let's talk about the planets. So shown here is the planet population. This is so if we pretend that planets, we don't include planets that were detected by Kepler, K2, and TESS. This is what the population would look like. So this is not a before and after. This is actually all other planets. This is plotted in planet. We have the planet size on the y-axis, orbital period of days in the x-axis. You can see that there's a lot of these. Oh, right, sorry. And the markers are colored by their detection technique. A lot of these techniques are easier for larger planets that produce larger signals. And even though we knew that, we still kind of thought that naturally we thought giant planets were still very common. And just as a reference, this is how Kepler and TESS, this is what a transiting exoplanet looks like. We've stared a bunch of stars and looked for these tiny periodic dips in brightness that indicate a bound companion. So now if we go back to this plot and now add Kepler and TESS detections, it was like a total game changer. So completely challenged everything we thought we had known about planet formation and evolution. And actually it turns out, if you look up here, you can see that Kepler actually told us that giant planet occurrence was actually quite rare at about 1%. And that the most common planet was between the sizes of Earth and Neptune. This was as shocking as it is abundant, because even our own solar system lacks an analog for this type of planet. So now I'm going to highlight all planets for which we have direct measurements. So that's it. So what do I mean by indirect? Basically, for all of the other planets, I'm going to flip back and forth a little bit. So basically, all of these other indirectly detected planets are found by changes in stellar observables that indicate a planet. Like for transits, this we just saw that it's actually proportional to the relative areas of the two objects. For RV detected planets, they orbit about a common center of mass. This means that literally all of the planet properties critically depend on stellar properties. So of the 5,000 plus planets we know about today, more than 99% of them are detected indirectly. And so everything that we learn about exoplanet science really critically, it hinges on host star, knowledge about the host star. And to really drive this point home, I'd like to share my personal favorite science story. So shown here is the Kepler field of view. When Kepler first launched in March 2009, there were 3 transiting planets already known in the Kepler field of view prior to launch. We have Trace 2b, Happy 7b, and Happy 11b. And because these were known prior to launch, they were designated the first 3 KOI numbers, meaning Kepler object of interest. As we all know, very soon after launch, the field of view was flooded with planet candidates. So the one that I'll be discussing is KOI 4, which is right here for reference. And again, because the first 3 were known prior to launch, KOI 4 was therefore the first new planet detection from the mission. So what I'm showing here is a measure of brightness in time, and we've just basically taken the period of the planet and folded it to that period. And this is centered on the actual transit. So the initial Kepler input catalog, or KIC, had classified the host star as a main sequence star, is a little bit hotter, but around the same size. A primary transit depth of about 1,300 parts per million would have implied a Neptune-sized planet orbiting a main sequence star. And now the problem with the classification is when a secondary eclipse was observed, the system was marked as a false positive. Basically, there was no way a small planet could create a detectable secondary like that. So I think they thought it was like a background eclipsing binary or contamination. But anyways, it was thrown aside and forgotten about because they had thousands of other planets to look at. So now insert me with my first year, apparently sending that email that really brought me back. This was in 2016, and this is right around the same time that Kepler just had this re-release of short cadence data. So they had recalibrated the data, and Dan had just done a catalog on astroseismic hosts. So he wanted me to go back through the data to basically confirm what we thought we knew, and then possibly find new oscillating host stars. And I did happen to find pretty low signal to noise oscillations in this star. So again, we have power on the y-axis and then frequency on the x-axis. I think this time I've added the time equivalent on the top for you. So as we saw at the sun, which was oscillating way about 3,000 microhertz, this is a factor of 6 lower. So it immediately implied a more evolved star. So in fact, our analysis figured out that the star was actually 3 times larger than initially thought, which therefore in turn made the planet 3 times larger, and now would be consistent with a hot Jupiter. And now secondaries, while they're still pretty rare, secondary for a close and hot Jupiter made sense. And this is actually perfect timing because I realized that I think that I just moved my poster, and so you can actually see this exact figure on the first one there. But sorry, for those in Zoom land, I've also included a photo here highlighting exactly where this image was. And this is with the man, the myth, the legend himself, David Latham. For those that do not know Dave, Dave has been a pioneer, truly a pioneer in the field of exoplanet science. So this was my first ever conference as a grad student. I was absolutely terrified. But you can see this, I'm cheesing really hard, and this is for good reason. I think this was probably before I learned it would take 2 years to publish too. So it turned out that Dave popped by the poster for a reason, and I'm only mildly fangirling there. Long story short, I mean, as you all know, applying or submitting abstracts and stuff for conferences takes time. So we had already applied for this. I'd already made the poster, but we ended up confirming the planet literally a week before the conference. And what he was doing, So as I was putting this talk together, actually, I was curious if I still had the original paper that he's signing. And sure enough, I do. This is what he was writing right down there. So he totally made it legit. It's confirmed. It was written by Dave Latham, right? So what did we do? Well, we did what any reasonable human being would do. We took it, printed it out, and literally tacked it on the board right next to the poster. So science. So again, I'm going to flip back because a very ambitious, optimistic first year student wrote Chontos et al. 2017 in prep, and we can't hide the publication date, but it took a full 2 years to confirm for many, many reasons. Dan likes to call this system the gift that keeps on giving, while I like to call it something else. We'll put this back here. Okay. So this did end up becoming my first author paper, where here I'm showing the MCMC modeling that I did for the planet. Again, this is similar to the figure I showed before. This is time from mid-transit for the primary, and this is the secondary. Zoomed in, you can actually, so these shaded regions are showing the duration, and the fact that the durations are not exactly equal was indicative of some sort of mild eccentricity, which was really surprising given the short orbital period. And then we have the full light curve shown up here in the upper right, and then the RV time series here confirming the planet. And despite the fact that the RV time series was so noisy, we were still able to measure fractional density to about 15%, which is pretty good. So because of the short orbital period and the fact that we had a 4-year baseline, we had hundreds of transits. And what you can do with that is you can measure the mid-transit time for each of those and then test for any sort of changes and when these times are, and when the transits are occurring. In other words, what we looked for was called orbital period decay, which is exactly what it sounds like, a decaying orbit. So is this spiraling in or migrating in towards its host star? Because for this system, we actually expect it to happen a lot faster. So I was sort of bummed initially, but ultimately we were not able to detect orbital decay in the system, but we were able to provide an observational constraint on the dissipation, the tidal efficiency of tidal dissipation in more evolved stars for the first time observationally. Yeah. Anyway, so KY4 ended up making for a nice story in the end because the confirmation came right around a decade later, around the time that Kepler was put to rest. As Dan said, we announced a discovery at the Kepler K2 Science Conference in Glendale, California. And I was reminiscing about this the other day, and I figured instead of sharing good press, I would share good bad press. So this is a snippet from Universe Today, and I'll admit they were off to a good start, and I quote, "Science is uber rigorous." You read this. Science is uber rigorous, of course, or it should be. Okay. We can't have false positives mucking up our data. No, we can't. And that's why it took them so long. Oh, wait, there we go. I'm mucking this up, mucking. And that's why it took until now to confirm the first exoplanet found by Kepler, known as Kepler 1658b. Great, agree. And then they continue. Kepler 1658 was first discovered with an emphasis on the first discovered by ground-based telescopes before Kepler was even launched. No, it wasn't. At the time, it was called KOI 410, where KOI stands for Kepler Object of Interest. It was literally never called that. And then the Kepler mission had already been planned, so they knew that this exoplanet candidate was in Kepler's field of view. That was like quite literally the entire point of the press release, is because we didn't. So then we also have a snippet here from the Cosmos where they got my name right, and then not the rest right. And then what's everyone's favorite answer to any time there's a planet discovery ever? It's definitely aliens. And then I'm saving the best for last because this one doesn't really need any words. It just doesn't work like that. So yeah, All right, well, anyway, so Kepler's first planet took nearly 10 years to confirm, which in this case was only possible because of the recharacterization of the host star using astroseismology. So hopefully I've convinced you that precise host star characterization is really important, because in some cases the planet's discovery depends on it. Right. So while Kepler taught us many things beyond our wildest dreams, another important takeaway was the critical importance of complementary ground-based follow-up methods, techniques. In fact, less than 10% of all Kepler planets have measured masses because the targets are so faint and difficult to follow up efficiently. Turns out there's another way that we can look at this by viewing the full sample of oscillating stars. So basically, I am showing something similar to what I showed with the planets, but now for oscillating stars. So here we're looking at the star size plotted by its distance from us, and markers are inversely sized by their magnitude, so bigger is brighter. As expected, pre-Kepler ground-based pre-Kepler discoveries were limited to nearby bright stars, but it was really difficult to do, and this is why there's really like only a handful over the course of like 20 years. But then again, Kepler, to save the day, added points. I think the numbers are, it's detected thousands of oscillations in red giant stars and about 500 in main sequence and subgiant stars. So while there were many points added, you can see that they're very small and very far away. And that's just further confirmation of that not just for planets, for stars too, having these complementary methods to like learn more about the systems is really important. Well, fortunately, there was little to no gap in NASA data with space photometry, as we already have the wonderful transiting exoplanet survey satellite, or TESS, up in a nice stable orbit with the moon. So here we see Cygnus constellation, and then we see Kepler's well-known mark on the sky. The entire Kepler field of view fits in just one TESS camera, and TESS has 4 cameras aligned from the pole to the ecliptic pole, almost to the galactic plane. And then we also have Kepler's repurposed mission K2, those marks there. And so TESS started with the southern ecliptic hemisphere, observing 13 27-day sectors, and then flipped to do the same in the north. So similar to Kepler, we're measuring star brightnesses with time, looking for transient or periodic phenomena. But dissimilar to Kepler, that only stared at very, very small, was less than 1% of the sky, we're now actually doing nearly an all-sky survey. So they're therefore sensitive to systems that are nearby and bright. So if we go back to this plot and add in TESS targets, you can see that it's nicely starting to fill in the middle region there, which is bridging the gap between the close by bright ground-based detections with the very faint Kepler detections here. Now for this bit, I want to draw your attention to the kind of subsolar like region here, which I've drawn a box for. You can see that even with the hundreds of main CO, with the hundreds of feet, there's still only a few detections in true solar-like stars. This is quite difficult because the oscillation amplitudes scale with the luminosity of the star. So we knew this was going to be difficult, especially with TESS. What we didn't expect was for TESS to be able to do this with nominal mission data. So within the first 2 years of the mission. So therefore insert accidental discovery number 2. AlphaMen is now the closest solar analog for which we have an astroseismic detection and characterization from space. It was literally the coolest star from the nominal mission for which we were able to do astroseismology. And one reason for this is because the Mensae constellation is in TESS's southern continuous viewing zone. This is a year-long light curve, which I've had the sectors down here. By the way, for reference, AlphaMen is it's a naked eye star with a visual magnitude of 5. And this is what the astroseismic detection looked like, shown in log scale here on the left, and then in linear scale on the right. So he also modeled the correlated red noise and white noise components, the summed model shown in the blue here. And before we actually determine astroseismic parameters, we subtract off the stellar contribution. That's actually what's shown here on the right. Then we take the shaded region where we think the oscillations are occurring and use an autocorrelation, which is just sliding the power against one another. Turns out based on the region of oscillations, you can actually fairly well predict what the spacing should be, which I'm showing here by the dashed lines, and we see really strong peaks there. So therefore quantitatively confirming the oscillations. And as we just saw with the sun, which had a new max around 3100 microhertz, here on higher new max immediately implied a later type star. And this was consistent with the G7 classification from an earlier paper. So there are many other exciting aspects about the system, which I encourage you to check out if you're interested. But in the interest of time, I'll say this. Since TESS is now pointed at much brighter stars, many of these, including Alpha Men, are very well studied and have tons of archival data readily available. So with little to no effort, and I say that in the most sarcastic way possible because I went down a rabbit hole that was over 200 papers deep, but it's worth it because I ended up finding an activity cycle of about 13 years using decades of archival data. So basically we had the astroseismic confirmation and then the activity cycle, like together confirming the like solar analoginess. And we didn't have to go out and get data for it. So yeah, the main thing, well, and to bring it back to planets, while there is no known planet orbiting Alpha Men yet, it's now one of the closest, best characterized, most well-characterized solar analogs. The distance of 10 parsecs, and it's therefore a prime target for the next generation of space-based direct imaging missions, hoping to image true Earth analogs around solar-like stars. So again, the main thing I would like you to take away from this specific TESS example is that the study precisely characterized two low mass main sequence stars, which is typically difficult to do, but did not require any additional efforts or observations from our end. In reality, though, this is not always the case, which is fine because TESS is still identifying bright nearby targets that are much easier to follow up. This means that TESS planets are much more amenable to RFV characterization and hence are easier to precisely characterize their properties. And remember, getting masses, let alone precise masses for Kepler, took an enormous amount of telescope resources if they were even sought after at all. Thus, TESS is establishing an ideal planet sample to better understand planet formation and evolution. This is where the observational component of my thesis comes in, which is just one aspect of the entire TESS Tech survey, or TKS for short. Implied in the name, TKS is a collaboration amongst partner PEC institutions to follow up, confirm, and characterize TESS planets. TKS was supported as a NASA Tech Key Strategic Mission Support Program, and yes, I did practice that, and collectively awarded 100 nights over 4 semesters. In addition, I had applied for, one of the perks of being a grad student here is being able to apply for institutional time. I was also awarded 16 nights over 4 semesters, in which I also pooled this with the collaboration, where the advantage to this, well, there are many advantages, but you know, you have different systems with different properties, different periods. You can get optimal phase coverage by following them up on different times that are not necessarily your nights. So I actually led the first TKS ensemble paper, which carefully lays out the scientific goals, as well as the detailed vetting and target selection steps. I will not bore you with those details, but the main thing I wanted to point out is that our paper highlights the importance of reproducible populations with a particular emphasis on RV surveys. This has been like a huge limitation for exoplanet demographics. What I mean by this is so often we might just drop a star if there's, we think there's a substellar companion, or if there's moderate V sin I, or a star with increased activity, which require you to throw some GP processing at it to disentangle the signal. Of course, this is all fine, but it's made survey selection functions very difficult to reproduce in later studies. So in the paper, we're actually completely transparent and provide our full sample. An example, which I'm showing in this figure, but it's nothing we haven't seen before. So on the top is an HR diagram. So this shows the TKS hosts. On the bottom, we're showing the planet size an orbital period again. So here, this TESS has 4 main science themes, which I'm showing right up here. And we have this sample that we selected broken down into these 4 science themes in which the targets were used to address specific sciences. I feel like I just here concentric rings represent targets that are going to be used to address multiple science cases. So in the work, I implemented a unique hands-off target selection algorithm that encouraged target sharing in order to maximize the number of planets that could be used to simultaneously satisfy all of the different science angles. So the overlap is actually even more clear in this Venn diagram, demonstrating the proof of concept. Venn diagram of four group is not. It took a lot longer than it looked. So the goal for making the software publicly available is that it can be applied to any survey which requires a balance of different science interests within a telescope allocation. So now for the rest of my talk, I want to focus on the obvious outlier in these parameter spaces, which is called TKS evolved, and is it's primary part of my dissertation work. It specifically focuses on TESS planets orbiting subgiant stars. But before I talk about the survey, I wanted to revisit our familiar friend and planet, KOI4. Okay, I swear I'm not misspelled. Okay. Yeah, it's another HR diagram. I'm really sorry. But we have the surface gravity here, effective temperature here. And oh yeah, I've also added some tracks just so you can see how stars evolve or move in these parameter spaces. In the context here, it was showing confirmed Kepler planets and then highlighting the Kepler astroseismic hosts. And the reason I bring this back up is because there was something I wanted to highlight that was kind of working behind the scenes that also helped make the precise system properties possible. And that's because the star sits in a very special region in the HR diagram as a subgiant. And to better show this, I'll actually break the sample down into evolutionary state. And because we don't just care about Kepler, we'll look at all of the planets shown here. So the purple group here is referred to as the main sequence. I know everyone here knows, but we have some people running on the line. So the main sequence is defined when stars are burning hydrogen in their cores. And for example, our sun is still in the main sequence. So it turns out that stars spend a majority of their lifetime on the main sequence, and specifically because of this, subgiants, which are shown in cyan here, provide a powerful tool to constrain masses and ages of host stars, which are otherwise difficult to do for, say, their main sequence counterparts. So therefore, because stars spend about 90% of their lifetime on the main sequence, even a location on an HR diagram like that shown here can be used to precisely characterize the host star and hence the planet properties. So as I said, this is for all planets, but now if we take a look at planets that have measured densities, so they have sizes via transits and then masses via RV detected, and we're actually back down to now under 1,000 planets. You can see that there's a majority of these are still main sequence stars, and that the subgiants and red giant stars are underrepresented. And this is for kind of a couple reasons. They've been notoriously avoided in surveys for the most part. There were a few earlier RV surveys focusing on this, but for the most part, people don't want to look at evolved stars, which is fine because then that means more planets for us, right? Well, just to name a few reasons why this is the case is because they're known to be noisier than main sequence stars. It's also harder to find smaller planets around larger stars. And we also know less, presumably, about post-main sequence star and planet evolution. So now I'm going to make a cut in the fractional density uncertainty. So now this was just all planets that have density measurements. So that you can see that the plot becomes even more scarce. So not only can we more easily measure system properties, but it's also an interesting group to study. So especially with the more recent discoveries of planets found orbiting white dwarfs, which indicate that the planets must be able to withstand some extreme environments. So this is just one piece to the puzzle, and was the motivation for why we ended up going after these systems. Okay, so we have our survey motivation. What's going on with the survey? If I had to summarize 2 years in a single plot, it would look something like this. That doesn't look very great, does it? Not for time series data anyway. Looks like some crazy systematics in there, definitely very noisy. Well, what if I told you is because you're actually looking at data collected over 2 years for 20 different planetary systems all at the same time? And I thought that was pretty cool. So this has been the last 2 years of my life. In fact, out of curiosity, I counted up just how much data was collected. And turns out that we had acquired over 1,200 high-res spectra. So yeah, it's a lot of data. So for the survey, RV data was fit throughout the course of the survey. We needed to continuously vet the systems, to make sure they were working, or even, like, if they weren't panning out, to make sure to drop them so we don't waste any more telescope resources. So now I'm going to go back to the same figure I showed just to put them in context. So again, I just moved the HR diagram over here. Now we're also showing again the planet size and the orbital period. And this is our sample. For numbers, there are 20 subgiant systems for which we have been extensively following up. Actually, that's not true. There are more, but there's 20 that are at a publishable level. Of the 20 that we have followed up, we have confirmed planetary nature in 28 planets, which immediately implies a fairly high planet multiplicity. I think this was one of the more surprising observational facts, in my opinion. And then all but 4 of the 28 planets have better than 5 sigma masses, so masses measured to better than 20%. And then 17 of these have 10 sigma masses. And I wanted to highlight this because actually our highest is at 43.7 significance. So we have some really good masses in here. But the 10 sigma was actually what we set out to do in our observing proposal. And we thought we were being very optimistic at the time, but we actually reached our goal, which was kind of nice to see. And I'm going to highlight a handful of systems to demonstrate some of the various camps that the systems fell into. The first is one of the fairly straightforward system. Just happened there. Oh, yeah, ranging anywhere from blatantly obvious to I absolutely have no idea. So the first is, we'll start with an easy one. This is TOI 1181. By the way, I don't know if you can see the yellow there, but I try to highlight which system I'm talking about on the population level. So TOI 1181 is super hot Jupiter, like very hot. It's sitting at an orbital period of just 2 days from its host star. So you can see that it's 16 times the size of Earth. And also its host star, for reference, is a little bit hotter. Panel A here shows the RV time series, the data that we collected, overplotted with the best fit RV model. And then you can see the phase folded RV time series here down at the bottom. This is a traditional hot Jupiter in the sense that it appears lonely and it's around like a younger, hotter star. And we really did try to look for and find companions for this star. And actually, because the V sin I was so high here, we could take what's called a Rosser-McLaughlin measurement, which basically checks for the alignment between the rotation axis of the star and the orbital plane of the planet, because this provides information on the past dynamical history. And for those that have tried taking this measurement, I had to include this because you can really appreciate it. For those that aren't used to these measurements, you're just looking for what looks like a sine wave. And you can see that this is just like the most beautiful RM signal I've ever seen. So I had to include that, sorry, but okay. So now going back to this, I'm gonna go to a little less of the system that was a little bit more challenging. This is TY 1294. This is another close and hot Jupiter at a period of 3.9 days. Here the host star is more solar-like with negligible rotation. It's a little bit older. And you can see that actually we didn't have much competition for this particular system. And I think I'm going to take a stab at why. So if you look down here, the plot here, we have almost a 9 sigma mass. But if you look at the eccentricity, that is highly unlikely given the orbital period of 3.9 days. So it just didn't make sense at the very short orbital period. And we continued to follow this up. And you can see that right here, we started having some like kind of offset. And after like the first few, I was like, okay. And then once we had a few up here, I was like, okay, that seems pretty convincing. So I just injected another planet at a uniform with the uniform prior, anywhere from like 1 day to half the total observation baseline. And we had a beautiful 2-planet solution with actually greater than 10 sigma masses for both of the planets, like just like that. And also there's indication for something else going on the system shown by this linear trend that is also preferred. So more to stay tuned. Okay, looks like I'm running out of time. So I wanted to show a planet. No, we'll skip over this actually. Okay, so basically, okay, so we have this wonderful sample that I'm currently cranking out the catalog for. And while program targets were not preferentially selected in that all we required was that they had an evolutionary state as subgiant status, we conveniently have a sample that nicely spans like all, different periods, different planet sizes. Doesn't show right, it doesn't look this way here, but some of them are metal rich and more massive. We have a star that's mass of 1.8, and they span a nice range and stellar properties as well. And the unique thing about the survey is that we're not just following these systems up for like confirmation, which is so often done with especially close and hot Jupiters. We're still continuing to follow these up. So we're probing long-term characteristics in these systems, therefore sensitive to eccentricities, the multiplicities of the systems. And I wanted to just end by following to show some preliminary ensemble results, starting with the mass radius diagram. So here again, we have a planet size on the y-axis, and now from RBs we get masses, right? And so that's what we're showing here. It's kind of hard to see actually now, but I wanted to see what the different populations look like in the mass radius plane. So now the sample is just kind of highlighted by the black circles, which are not really. Anyway, the thing that I wanted to point out that I thought was very interesting is this dearth of planets, of larger, more massive planets around occult stars, because the bias wouldn't work that way. These are easier planets to detect, but they're just not there. And this is consistent with predictions from tidal dissipation theories. But it was, it's definitely good to see. And while I'm not quite convinced yet, because the numbers are still small, we kind of see what might be a tighter sequence for smaller planets around involved stars. So again, still preliminary, but. And then another place where the survey stands out is its ages, right? So So when we refer to tidal dissipation, I was talking about in the context of orbital period decay, but there's also a circularization process. And so therefore, if we have ages and eccentricities, maybe we can say something about how quickly these processes occur. So now, to be honest, Dan and I had speculated what we thought this would look like, but really had no idea. Maybe starting with a wider range of eccentricities for like protodynamics early on, and then as they age, circularize and go to more modest eccentricities. And it turns out that that is not what we saw. So here is the planet eccentricity and age in gig years, and then we've colored the points by its orbital period. And it's not really, there's not much we can say definitively about it, but some of our most eccentric planets are around some of our older stars, which was just, it was surprising to see. So I'd also like to try to make this plot with stellar mass, maybe planet multiplicity, maybe even predicted timescales with respect to how old they are. But yeah, again, preliminary results. I've only just started digging through the thousands of RVs that we have, but I'm very excited about this. And in the interest of time, I will stop because I have to many people to acknowledge here. So Dan, what do I say? Yeah, I clung to you as soon as you got here and you couldn't get rid of me. So we're close, right? No, I honestly cannot express how much gratitude I have. You were so patient with me, and this was new for you too. And you were just an amazing advisor. And Sarah's another one on the line. Sarah, you took me under your wing, and even though you didn't have to, you let me experience TESS at MIT and have really helped with, my confidence. Yeah, and I love that you just tell me what I need to hear. Also to my committee, who I'm pretty sure is calling in from 4 different time zones. I'm so sorry, Kim, you're a trooper. Kim, I think it's 10 p.m. or now 11 p.m. for Kim. Also, Jenna's on the next line because you deserve a special shout out as my faculty mentor and for believing in me when I didn't believe in me. So, and then I have a bunch of other instrumental, as Dan said. Bruce McIntosh was very, pivotal and was my first experience with astronomy. And that was when I learned that you can get paid to go to grad school. So here I am. Of course, over 70 nights, many interactions with all of the amazing tech staff, the essays, the TOs for putting up with me for over 70 nights. Andrew, the CPS, allowing me to join the CPS collaboration, the TESS survey collaborations, getting all the wonderful people there. I really appreciate that. Task is still the coolest community in my opinion, but I'm just saying. Yeah, and then what I call my IFA angels, Amy, I know she just left, but here, Laura, Melissa, Carolyn, Kaiichi, honorary member JD, all the IFA outreach at Hona. They make the IFA a better place. And then my classmates, good luck tomorrow, Zach. It's only proper we go out together, right? And then also Dan's research group, which we have some honorary members who have now also left, but is arguably like my favorite meeting every week, and I learned so much. And then computer services, we had a very interesting week last week, so I appreciate all the help. And there's just, I didn't even highlight this, but there's so many wonderful IFA students here, so love you all. Friends and family, Dad and Diane, Nan and Pop, I know you guys would be here if you could. I love you. And of course, my emotional support child, Sarah, who's probably off in New York sleeping for me to make up for all the losses that I've had. So, yeah, I think that is all I have. So I'll leave these up here and take any questions. Thanks for listening.
Okay, thank you, Ashley. We have time for questions. A little bit over the time, but we'll make time for questions. So any questions in the room? Nick.
Hey, Ashley, great talk. So many exciting results. I was curious about the eccentricity distribution stuff you talked about at the end. I know it's all preliminary, but I was curious if you see any dependence if you look at specific orbital period bands? Like, do you see that trend you expected if you just look at the short period planets where you might expect tidal effects to happen faster?
Yeah, that's a great question. And like I said, this was there. Well, the first problem is this is kind of like just small, very small sample at this point. I haven't been able to kind of dig through the exoplanet archive and add all other similar ones and properties that I trust more importantly. So there is an interesting thing I found with actually the giant planets. I'll probably take too long to discuss, but yes, if I put this if I only plot this with giant planets, there's some very interesting thing in that all of the circular hot Jupiters are young and all of the eccentric hot Jupiters, and they're around like a period of like 8-9 days, are eccentric and less than 1 Jupiter mass. So there's something I think I start seeing to emerge from at least hot Jupiters, which might help elucidate like what's going on for how they form and evolve. I think I just went off on some other, not sure if that was totally fast, but yeah, if you have ideas on, we can definitely chat about that.
Thank you.
All right, more questions?
Yeah, that was a really interesting talk. It's totally outside my field, but I was curious. I'm always interested in sort of the overall context of the field. So, you know, you have this great TESS satellite and all these people from the ground following up the systems. So I just wondered if you could talk a little bit about some of the other experiments that are being done, like the NUID instrument on the wind telescope. I know there's some work being done in Texas. Like, how does that, are they complementary? Are you all kind of doing the same thing? How does that all fit together?
Yeah, yeah, great. That's a great point. There are definitely other, I feel like TESS more than ever is now a very community-driven program. Like we have the TESS follow-up program, which is where other places like, you know, we have collaborators at Trace Telescope. There's also the Magellan TESS survey. There's many ground-based TESS RV surveys, and we all try to collaborate together. It doesn't always happen as nicely as that, but basically, I feel like it's more of we try to work together than, you know, duplicated efforts. So we have, you know, we're just always in contact with, you know, for a lot of these planets, I've actually been coordinating with other people also following up those systems. It's definitely oversubscribed in that sense, but yeah, everybody tries to do their best to work together.
There's also so in terms of new instruments, right? There's KPF that's upcoming.
Oh, right, yeah, yep. Yeah, Andrew on my committee chairs, we're just talking about how that's on 2 boats somewhere, so that'll be coming online, and high-res will, yeah, they'll be taking over high-res.
That's been. Have you looked at, very nice talk, the question is similar to this, but have you looked at Roswell McLaughlin as a function of age for these particular planets? Like basically, are they inclined in a different way relative to the stars? Maybe it's more difficult because the stars are more evolved to the larger synopsis.
There was actually, there was a plot in the TESS survey paper that I was talking about before, and I'm trying to see if I can find it. But basically, we did look into this because the tides, you know, operate on like giga-year timescales, but then there's cosine up and other things that happen at you know, different points. And I think most of the earlier work has been done with like clusters for which we can get really well measured ages. But the idea was to try to do that with and with this and compare it to, because we have the nice ages, to try to compute like what the circularization timescale and what these other timescales would be and see like where they are with respect to that. But I forgot that. I don't know. I don't think that answered your question.
So it seems like it's ongoing. So so you are looking at the Roswell McLaughlin as a function of like age, because obviously you mentioned the dynamic.
That is, yeah, that's like the next step, and that's something that Nick's been thinking a lot more about than I have. We ended up just getting it for the one a target, but there are actually there are several systems for which we can actually measure that, but there's one, we have this eccentric warm Jupiter. It's at a period of 45 days and its eccentricity is 0.5. This is very eccentric. And being able to, and it's transiting, so if we can measure, right, like comparing warm Jupiters and how they are aligned or misaligned with respect to the hot Jupiter population, it might say something interesting about how they're getting to their present location. But yeah, haven't really gone that far yet.
Yeah, let me ask on Zoom land, are there any questions? I think you're allowed to unmute. So if you have a question, please unmute and fire away. I don't see any hands up. I'm not sure if that works.
I'm gonna take a minute to.
Okay, are there any last questions in the room? Oh, there's a hand up. Over there. Alex, go ahead.
Hey, yeah, actually, no real question, actually. I just want to say thank you for that awesome presentation. It's great.
Thank you so much for calling in, Alex. It's another great TKS crowd.
Okay, well, if there are no more questions, then let's thank Ashley again.